So the next speaker is Matías López from Instituto de Física de Pontificia Universidad Católica de Valparaíso, who will talk about chaotic inflation in non-minimal coupled scalar-tensor gravity theory with Galilean self-interaction. So please, you have 15 minutes plus 5.
Okay, thank you. So, first of all, I would like to thanks to the organization for allowing me to present this work. And I've been doing from the last year. My name is Matías López, and I will be the speaker of this presentation. And this project um, was worked with Giovanni Otarola, postdoctoral researcher from Pontificia Universidad Católica de Valparaíso, and Nelson Videla, who is my advisor teacher in my master in physics. So, for practical purpose, this presentation will follow the next order, and hope you understood easily the main idea. So, first of all, I would like to present here why has been proposed through all these years this particular idea of a primordial accelerated expansion, better known as inflation, just before the moment we know as the Big Bang. Our standard cosmological model predicts successfully some properties of the observable universe. The existence, for example, of the cosmic microwave background, the distribution of large-scale structure, some remnants, some heavy metal remnants like helium or deuterium, etc., and the light-time accelerated expansion of the universe due to dark energy. But the problem with the standard model is that it can explain the nature of some observable quantities. It detects, for example, an spectral index predict to an almost Euclidean form of the spatial sections. And at last but not least, it detects super horizon signals of the element that creates the anisotropy seen in the cosmic microwave background temperature. So, in order of trying to give a physical explanation of these issues, cosmic inflation was proposed. And let me explain the mainly idea. This goes as follows. First, the most simple form of matter that makes an accelerated expansion in the early universe is quantified in a scalar field that changes in time. The field is homogeneous at every point, so in every part of the universe, the rate of expansion will feel the same. But the field has fluctuations, and these fluctuations can appear at random places or points of the space. And these fluctuations can be quantized and exist in an expansive background, so their wavelength will increase from small scales to super horizon scales within an superluminational speed. So a direct consequence from Einstein field equation says that if there is fluctuations in matter, there will be, of course, perturbations over the space. And these last perturbations in the metric, specifically when they reach a super horizon wavelength, will be important in the stage of inflation where the potential energy is dominant and almost constant. You can see my cursor just right here till here, I think. In other words, this is the stage from here to here where the primordial cosmological perturbations were born. These last quantities the perturbations can be qualified as three scalar, vectorial, and tensorial forms, but the first one has an important advantage. The power spectrum of the scalar perturbations and its scalar spectral index already has observationally constraint measured by Planck in the last years at least. And it also has a constraint over the tensor to scalar radio. Let me tell what is this. Uh, this is a quantity read as the reason between the tensorial perturbations power spectrum and the scalar power spectrum. So this quantity is useful to detect primordial um, gravitational waves, okay? But our interest in the chaotic potential is because, as you can see in the black line here, our interest in the chaotic potential is because it is in actual tensions with the observationally constraints measured by Planck in the last years. This is the latest constraint by Planck. So um, with the Miley idea, first, let me tell you how we try to predict an early universe scenario. So first, we start from Hordesky theory, but we need some previous knowledge because it will be useful to interpret the predictions that we have with our system. So from Hubble's law, it can be defined a new parameter called epsilon, right here. This parameter is known as the slower parameter most of the time, and it parameterizes an inflection point for the accelerated form of expansion of the universe, right here. So as you can see, if epsilon reach 1, the acceleration will reach a value of 0, and because the epsilon parameter depends at least, well, in every time, but in the standard general relativity, depends on the kinetical energy of the field, inflaton field, and depends respect to the potential energy too. The epsilon parameter will tell us where inflation ends and in some scales of energy. As I told you before, the perturbations that has already a constraint, an observationally constraint, um, occurs in a limit. This limit is the slow roll limit. So the Fields equation, like the Friedman equation, Clay-Gordon equation, and the barotropic parameter, can be approximately this. So let me explain what is a number of equals, because this will be our principal parameter. This is an amount of growth of of the space between two stages of the cosmological history. So let let me um, tell you how we work from here. Um, so the question is, how we load the scales of energy raised by the chaotic potential? First, we have worked with the Horndeski theory. This is an extension of general relativity and the most general tensor scalar theory in gravity that already raised second-order equations of motion. It is known from this Lagrangian that it avoids Ostrogradsky instabilities. This is good. So on the other hand, um, by observational constraints coming from gravitational waves, this Lagrangian reduced to only non-minimal coupling. Right here, we use this definition for the non-minimal coupling to gravity. Some quiescence, we use here some classic quiescence that is the difference in this case between the kinetic energy and the potential energy, and we use some Galileon cubic term, but in our case will be this. So one of the equations that can be derived is the Klein-Gordon equation from an expansive universe. We see first that this equation suffers a modification, a little modification, because we introduce some friction new term that is identified with the Galileon term right here. And it will be another friction term from the non-minimal coupling to gravity right here. So, and well, we will work with the chaotic potential. So we can define two free parameters for this system. One is the non-minimally coupling constant right here, chi, and the
Sorry,
second one,
Matthias, you have 5 minutes left.
okay, and the other free parameter is delta, defined by the ratio of the amplitude of the potential and the mass scale for the inflaton. We will work with p equals 2. So let me show you how we predict some viable early universe scenario from the Planck region of confidence. So let me tell you first some little algorithm. First, we try to get an analytical expression for the inflaton field from the number of efforts, but this integer is extremely non-analytically, so we have to work with some differential equations for the field. The initial conditions come from the condition of epsilon equals 1. So then, because we know how to derive the expressions for the scalar perturbations power spectrum, and because we know it has some observational constraint, we can express the amplitude of the potential in terms of the free parameters of our system from the number of evils and from n. Well, this is a mistake. This is the power law right here, P. We can study the observationally inflationary quantities, that these are the scalar spectral index and the tensor to scalar ratio in the region of confidence of Planck. So the first results are right here. For example, this is for the chaotic potential with the power law equals 2. So this red line is the standard general relativity prediction for this potential. We can see that is out of the minimal region of confidence from Planck. So the way we fix this was growing the non-minimally coupling constant, as we can see, from 0 comes from the red line, and when we grow the non-minimally coupling constant, this down the tensor to scalar ratio right here. So these yellow lines are some general relativity like results, but if we increase delta to the other free parameter, we will see that it affects only in the scalar spectral index, because it will turn from the left to the right. But we see that the more sensitive free parameter that we have is the non-minimally coupling constant, because it loves the tensor to scalar ratio and it loves the scalar spectral index, as we see here. So, but we had an issue. We don't find bounds for our free parameters, so we had to solve the complete equations. These are the Friedman equation, the Raychaudhuri equation, and the Klein-Gordon equation for non-minimally coupling with Galilean self-interaction system. So we define some adimensional parameters in order to have some closed differential equation system, and we study the oscillations of the inflationary quantities at the end of inflation. And how we start this? First of all, we started with the square speed of the scalar perturbations. Let's remember when this parameter is 1, then the scalar perturbations travels at the speed of light. So, but as what we see here, if we got the Galilean term affecting the system, we see that at the end of inflation, some oscillations start. For example, for these values for the free parameters, we reach some square speed of the scalar propagation at the end of inflation. We reach that it oscillates and reach a zero value right here, but we can reach a maximal values for our system, denoted by the green lines. These are the values, the maximal values for the free parameters that don't make the square speed of the scalar propagation uh, diverge to the minus infinity. Or in other words, these are the maximal values for our free parameters in order to avoid Laplacian's instabilities. So another implications right here, for example, for the Q sub S parameter, it is known that it always have to be positive. So for example, for this choice of the free parameters, uh, we see that we avoid the Laplacians, the other condition for to avoid Laplacian instabilities, and we can see here to how it affects to the inflaton field. For example, um, the existence of a non-minimally coupling constant and a Galilean term lowers the scales of energy of the inflaton field, because in the general relativity limit, it is like at least when the scalar perturbations cross the horizon, 16 epochs before inflation ends, in general relativity, the inflaton field reach a value of 15. So with this parameter, we are in 8. So this is a good news because as a consequence of lowering the scales of energy, we lower the tensor to scalar ratio. And we can see that the oscillations had a duration of more or less than 6 or 7 epochs. Um, another implicance of the, for example, if we fix the value of delta and if we grow the non-minimally coupling constant, we can see that the duration of the primordial acceleration accelerated expansion of the universe is more longer. And for the maximum values that our free parameter can reach, we see that it is still, for the inflaton field, it is still reach some Transplanckian values for the field. And we see here that if we grow the free parameters, the oscillations of the field are more longer. And well, in order of time, I will not talk so much about the epsilon parameter that defines the end of inflation, but um, well, it oscillates respect to 1.5, and this is interesting because well, I prefer not to talk much about that because I don't know how, very well how to interpret this yet. So the summary of this, and to end my presentation is, in this system, the chaotic potential can be completely variable if there is an extension of standard general relativity. There was not possible to find maximal or minimal bounds to free parameters in the, well, in scalar spectral index, and, well, let's just say the region of confidence from Planck. And because of this, we had to study the oscillations. It was possible to find just maximal bounds, and we could estimate these values looking over the cosmological perturbations quantities. And because the Galileon or the non-minimal coupling uh, co constant, yes, are non-dominant in scales of energy, Laplacian instabilities can be avoided. So this opens the opportunity to study reheating after inflation ends. And some reference. This is the principal reference we base it for this study. And thank you so much for your attention.
Thank you very much, Matías. We are almost in time, but we have time for perhaps one quick question or comment.
Mm-hmm.
Is there any question, comment? I have a very naive question, if there is no question. What is the
Okay.
main difference between chaotic inflation and non-chaotic? How do you, what is the signature of chaotic inflation?
Okay. Um, the signature of chaotic inflation can be seen here, because concavate potentials have a more favorite um, uh, values, or are in favor to the respect to the predictions from Planck, and the chaotic inflation can be seen here, just out of the minimal region of confidence.
Okay,
That is the signature of the chaotic inflation. It reached extremely high values of energy.
okay,
So that's why we wanted to low the scales of energy using Horndeski theory.
okay.
Mhm.
Thank you, Matthias.